Now we'd like to welcome our speaker, Professor Moore has a PhD in geophysical fluid dynamics from Princeton University. He is a professor of physics and vice principal research at the University of Toronto, Mississauga. Professor Moore's research interests include theoretical geophysical fluid dynamics, mesoscale meteorology, polar meteorology, high latitude air-ice-sea interactions, physical oceanography, paleoclimatology, and high altitude physiology. Professor Moore has published over 170 research papers in peer-reviewed literature, including papers in Science, Nature, Nature Climate Science, Nature Communications, the New England Journal of Medicine, and the British Medical Journal. Please join me now in welcoming our speaker, Dr. Kent Moore.
Thank you. Okay, thank you very much, Betsy, for your introduction, and thank you for this opportunity to give this presentation. I'd like to start by acknowledging my collaborators on this work, Steve Howell and Mike Brady from Environment and Climate Change Canada, and Caitlin McNeil and Xiaoyang Xu from the University of Toronto. So I'm going to be talking today about ice arches that form along Nares Strait. And I want to start off with a video which shows one of these arches and its collapse. So we're sitting here, this is Ellesmere Island over here, Greenland is over here. So Nares Strait is this strait here between Ellesmere Island and Greenland. This is a video of some SAR imagery. We're going to start on April 1st, 2017. We're going to run through for about 2 months. And so early in the winter of 2017, an ice arch formed here at the northern edge of Nares Strait, and it was stable for about 4 months or so. And so when we start the video, you'll see this arch will remain stable. There is new ice forming in Nares Strait. It's the winter, of course, there's open water, so one is getting ice formation. And this ice will flux down through Nares Strait. This is mostly, very, very young ice. And then eventually around the middle of May, this arch will collapse and suddenly all this really old and thick ice will start flowing down Nares Strait. So here's the animation. You can just watch the date up here in the corner. I see how stable the ice is north of the arch. And then about now, wow, there it goes. I'll just run this one more time for you. So again, there's winds blowing down the strait mostly. So one is essentially ejecting all this young ice down through Nares Strait, but the arch remains pretty stable. And then there it goes. It collapses. Okay. So we're all aware that the fact that there's a reduction in Arctic sea ice extent, but there's also been a thinning of the ice as well as an increase in its mobility. So these are 2 time series. This is some Polynyas data. This shows essentially winter mean ice thickness north of 70 degrees north. And you can see over the last 40 years or so, there's been this dramatic reduction in the thickness of the ice. And this is ice motion. And you can see, again, there's been this increase in ice motion. So we're seeing a transition not only to a reduction in ice extent, but also a thinning and an increase in the mobility of the ice. And so in this talk, what I want to do is I want to explore the impact that these changes are having on the ice dynamics along Nares Strait. So again, just to give you a bit of a background, this is climatological annual mean ice motion in the Arctic. We're showing essentially the magnitude is shaded and the vectors are the ice motion. And so one has, again, the basic sort of characteristics are one has this Beaufort gyre over this anticyclonic motion in the Western Arctic, transpolar drift, which then shoots the ice down here through Fram Strait. And then one has these 2 regions where ice is leaving the Arctic through Fram Strait and also down through Nares Strait and the Canadian Arctic archipelago and then down through Baffin Bay. This is ice age data, and the white contours indicate the oldest ice in the Arctic, which is older than 5 years old. And so what you can see is that, and again, this is I think the climatology is based on 1984 to 2020, and one can see the oldest ice is here up against the Canadian Arctic archipelago. And as one transitions across the Arctic, one is getting into essentially first-year ice here and then essentially second-year ice in through here. And so the important thing is that Nares Strait here is situated in this region where one has the really, really old ice in the Arctic. And so when we have transport down through Nares Strait or the Canadian Arctic archipelago, we're really losing the really old ice out of the Arctic. This, again, is data from Polynyas showing thickness. So thickness is just another way to explain the age of the ice. And again, you can see that the really, really thick ice is up here against the Canadian Arctic archipelago. And this region is now referred to as the last ice area, because this is the area where presumably ice will persist through the middle of this century, and it'll provide a refuge for marine dependent species. And again, Nares Strait's in this very strategic location, just essentially the export of this really, really thick ice out of the Arctic. So the World Wildlife Fund, for instance, started calling this area the last ice area, this region of the very, very old and very, very thick ice up against North Greenland and also the Canadian Arctic archipelago. And this is of importance because it will be the area that loses the ice. The perennial ice will be the last to be lost in this area. And so it will provide refuge. The Canadian government has recognized this, so they've essentially established a marine protected area, essentially in part of the Canadian last ice area. I can't pronounce the Inuit name for it, but it's called the place where the ice never melts. And so this is really in recognition that it's a very special area, and we need to protect it moving forward. So Nares Strait, the export down Nares Strait is really seasonal. It typically ceases around December when an arch forms either the northern end or the southern end of the arch. And that arch typically remains in place until about July or August the following year. So the pioneering work in this area was done by Ron Kwok and his collaborators back in the about 15 years ago or so. This is a time series of ice export through Nares Strait. So positive values mean southward transport. And you can see that the transport is variable through September through December. And then in this case, this is the year 2000, around January 4th, an arch formed. And then essentially the transport went to zero. There was no transport at all until July, when the transport picked up again. So this is a typical seasonality that we see transport during the fall and early winter, and then when an arch forms, the transport goes to zero for a significant amount of time. In the Kwok data set, which runs from 1999 to 2010 or so, there was only 1 year where an arch didn't form, and that was the winter of 2007. And this year there was a significant export of ice down through Nares Strait, and Ron Kwok suggested this contributed to the loss of multi-year ice that year from the Arctic. This is, again, data from Kwok et al. 2010. So we'll just focus on this black curve here. This essentially is the annual ice flux. And you can see 2007 here was the highest year, and this was the year where no arch formed. So in this year, there was significant transport of ice. It makes sense if the arch doesn't form, then one has transport the whole season. And so one got a very, very large transport down in 2007. So just to kind of remind you of the kind of geography and the topography of the region, this is the Nares Strait region here, Ellesmere Island to the west, Greenland to the east. The topography is quite steep. One can get elevations are typically 500 to 1,000 meters along the strait here. And that leads to a very pronounced directionality in the flow. The flow either goes down the strait or up the strait. So essentially, this is very strong topographic channeling. We are going to look at ice fluxes across this flux gate right here, which we established just sort of north of Nares Strait in the southern Lincoln Sea region. We'll also have a couple of other flux gates that we'll have farther south. One essentially trying to capture the transport down here through Smith Sound. So that we have a couple of different regions that we put flux gates in here, depending on exactly what we want to look at. So this is an example, the example that I showed you in an introductory video. This essentially is MODIS imagery. This is April 17th, 2017. You can see the ice arch present here, again, with the thick multi-year ice to the north, and then essentially thin ice down through Nares Strait. We'll be looking at some automatic weather station data from Hans Island. Hans Island is an island which is right exactly in the middle of the strait, down about just south of 81 degrees north. This is an image essentially on May 18th, about a month later. You can see the arch is now collapsed, and one can see essentially the the sort of very kind of fragmented nature now of the ice north of Nares Strait, and some very large ice flows coming down through Nares Strait. At the southern end of Nares Strait, one has the North Water Polynya, and as we'll see, that the North Water Polynya is crucially dependent on the formation of an ice arch at the south of Nares Strait in the Smith Sound region right here. And this can be shown here. So this is a satellite image of a southern ice arch. So here's Kane Basin, Ellesmere Island, Greenland, and the ice arch formed here. And then essentially there's very, very strong winds that blow down Nares Strait essentially advect any ice that forms this region southwards, leading to this presence of this Polynya to the south of Smith Sound called the North Water, which I think is the most productive Polynya in the Arctic. And again, if one doesn't have this arch present here, then in fact one can have ice fluxing down, multi-ice fluxing down through here, and that can cause problems for the Polynya. So in this talk, I'm going to be using atmospheric data from the ERA5 reanalysis, as well as there's an ensemble member which has a lower resolution, and it's important to look at the impact of resolution on the representation of the flow. We'll also use the current operational analysis from the European Center, which I call the ECOA. We'll use sea ice concentration data and ice motion data from the AMSR series, Sentinel-1, and also SSMI. We also use sea ice data, concentration, thickness, and mass balance from biomass as well. And we'll also look at some automatic weather station data from Hans Island, which is in the middle of the strait, and also Cap Morris Jessup, which is in North Greenland. And these are some polar bears visiting that automatic weather station at Cap Morris Jessup, and there was some unscheduled maintenance they were doing on the weather station, and this is one of the, I guess, one of the challenges of working in this area, and so they trashed it out. This is Hans Island. It's a island that sits in the middle of Nares Strait. This is actually Ellesmere Island off in this region here. This is a Sentinel-2 satellite image, and that's Hans Island right in there, right in the middle of the strait. In fact, it lies right on the boundary between Canada and Denmark, and this has led to some challenges as to who actually owns the island. In fact, there are times when the Canadian forces have landed on the island and raised the Canadian flag, and there's times when the Danes have landed on the island and they've raised the Danish flag. So I think Canada and Denmark have agreed to not agree on who owns the island, because there's bigger fish to fry, who owns the Arctic Ocean seafloor to the north. And so I think they're cooperating in claims as to sovereignty over the Arctic Ocean seafloor, and they decided just to not really force the issue who owns Hans Island, because it does sit right in the middle of the strait. Fortunately, science doesn't have to deal with issues of political jurisdiction, and so a group of Canadian, Danish, and American scientists installed a weather station on Hans Island in 2012. It has operated since that time, although it's not functioning right now. It's an incredibly challenging environment, and it stopped working sometime this last fall. And so the first question I want to do, because it's important to understand the winds, because the winds do essentially impact ice motion down the strait. So how well do models represent the variability in the wind? And so what I want to do here is I want to look at 3 different versions of the ECMWF's integrated forecast system. I'll look at the ensemble ERA5, which has a resolution of about 50 kilometers. There's an unperturbed member of this ensemble, so I'll just look at the unperturbed member. And then the ERA5 has a resolution of about 25 kilometers. And then the operational analysis has about resolution of about 9 kilometers. And so what we did essentially just looked at the ability of these 3 models. They have the same basic physics. So essentially the basic physics of the model is the same. So any differences we see in the representation can be put down to essentially the resolution, because we're controlling for the physics. And so it's really just the resolution that we're varying when we look at these 3 different versions. So these are scatter plots. This is data from 2016 to 2020. So I'm just looking at wind speed here. So the observed wind speed is plotted on the x-axis, the model wind speeds on the y-axis. I have a bunch of statistics up here. If the fit is perfect, the data should lie along this line, y equals x. And you can see that especially for these lower resolution data sets, the fit is actually quite poor. The correlation coefficient is not bad at 0.67 or 0.79 or whatever, but the slope is really, really low. Of course, and what this means when the slope is low is that the really high wind speed events on Nares Strait are being under resolved in the models. When one gets to the 9-kilometer model, it's actually better. The slope is now 0.8. And the RMS area, for instance, is down by almost a factor of 2. And so we see this steady improvement in the representation as we go from the 50-kilometer product to the 9-kilometer product. And I'd argue that really it's only the 9-kilometer product that has essentially it does a good job of capturing the variability. But of course, 9 kilometers isn't quite there yet, because then there is still this mismatch, especially at the high wind speed events. The weather station is at about 200 meters above sea level. And so I'm looking at 10-meter winds here. You could say, well, what if you looked at the 100-meter winds? Because clearly it's not really surface flow that you're actually resolving. And if you look at the 100-meter winds, they do a better job, but the basic physics of the fit is the same. So I don't think it really makes a difference whether you use the 100-meter winds or the 10-meter winds to do this. And so it's maybe not surprising to get this result. Around Hans Island, the strait's perhaps 50 kilometers wide. And so clearly models which have resolutions in this scale aren't going to be able to represent the flow. One needs to get down to resolutions of, let's say, 9 kilometers or higher to represent the flow. The problem, of course, is with this operational model, one only has a few years of data. So you can't really get good statistics on the wind. ERA 5 has essentially now almost 70 years worth of data. So it's much easier to get good statistics, but one has to realize that one is essentially underrepresenting the wind speed. So now I just want to essentially step through and look at some of these events that have happened over the last few years. Again, we've shown this image before. This is before the collapse of the ice arch. This is after the collapse of the ice arch. This is thickness data from biomass over the southern Lincoln Sea. And so what you can see is that in 2017 here, the ice was actually quite thin. Okay, there's again been this remarkable reduction in the thickness of the ice over the last 40 years. And 2017, the ice was quite thin. It got thinner in 2018 before it bounced back, but essentially the ice is much thinner than it has been in the past. So this is a time series now of ice area flux. So this essentially is the area of ice fluxing through past that flux gate. Southward is positive transport. So essentially when we have positive values of ice area flux, we have southward transport. And I'm plotting here the wind speeds. This is from the 9-kilometer product. And you can see this remarkable transition that occurred around May 10th. So before May 10th, the fluxes were very, very small. And then suddenly on May 10th, the fluxes increased by at least an order of magnitude. And this was the collapse period right here. But there are all these sort of little spiky events here, even after the collapse. And so if you line up these spiky events with the wind speed maxima, you can see that most of the times there was essentially the wind speed maxima preceded the peak fluxes by a few days or so. And what's important is that this high-speed wind event around May 10th, which was a 2 sigma event, so pretty rare event, in fact, was the one that was associated with this collapse of the arch. So we had thin ice present. We also had anomalously strong winds in 2017. And so the question is, did those two contribute to the collapse of the arch? And there's been some work done on this. Bill Hibbler did some work about 15 years ago or so, looking at essentially very simple models of sea ice arching and what controls the presence of an arch or not. The model is really simple. One essentially has an open boundary here with some sort of area where the flow is being constricted. One applies a uniform wind field across here and then considers steady state plastic flow solutions for this domain. These are the results. So there's 2 states to the model. When the ice speed is 0, that means there's an arch present. And when the ice speed is greater than 0, there's no arch present. And so essentially Bill ran this model for various wind speeds. And what you can see is that at the higher wind speed, the 9.8 meters per second, the arch collapsed for a thickness of about 2 meters, whereas if you ran an 8 meter per second wind through this domain, the arch collapsed about 1.5 meters. So higher wind speeds result in the collapse of the arch for thicker sea ice. And so this then leads to the conclusion that thinner sea ice and higher wind speeds should lead to weaker arches. So it's possible that the thin ice in 2017, along with the very strong winds, did actually contribute to the collapse of the arch. And again, this is just this time series. I'm going to look at now a few events before and after the collapse, which occurred again around May 10th. So these are Sentinel-1 SAR images, and what I've overlaid here are sea ice motion vectors that were created by using essentially a feature tracking. So we looked essentially at, two images, let's say a day apart, and then one tracked the features on them, and from that one can infer ice motion. The flux gate is shown here. And so this is before the collapse. You can see there's no motion anywhere in the domain. May 10th, the arch started to collapse. You can start seeing essentially some ice motion now as the arch begins to collapse. 2 days later, the collapse was full on, and one had essentially ice motion upwards of 20 kilometers per day or so, fluxing southward into Nares Strait. And then again, 2 days later, again, one can see essentially an ever-expanding region where the ice is now has been fractured and started to move down through Nares Strait. So these collapses, when they happen, are really, really dramatic. The arch can stay stable for months at a time, and then it just suddenly collapses in just a few days. So Sentinel-1, we have data from September 2016. This actually runs through until the middle of January. And this is the time series of the daily mean ice area flux across the Lincoln Sea flux gate. Again, positive values mean southward transport, negative values mean northward transport. There are sort of a number of events where the transport gets very, very small. This is the arch formation in 2017. This is another arch formation in 2018. There was no arch present in 2019. So throughout the winter of 2019, as Kwok found in 2007, the transport was non-zero throughout the whole winter. We had an arch form in early 2020, and then an arch formed just in December 2021. So these essentially is the full record that we have now of ice area flux. What's quite surprising when I first started looking at this was that one get these not only, so on average, the transport is southward. So these are the averages over these various periods. So there is southward transport, but you can see that almost through all these events, one has essentially episodic events where the transport is actually northward. So we actually are pushing ice up into the Lincoln Sea from Nares Strait on occasion, and we'll focus on one of these events that happened just in early 2021. So this is quite interesting. Also, if you look at these arches, so we have these 3 arch events happening here. These arch events, what I would say would be what I would call leaky. So even though there was a dramatic reduction in the transport, there was still essentially ice fluxing back and forth, even in these events where there was an arch present. The arch in 2020 is quite different. It was bang on zero. There was no transport at all. And we'll actually come back and look at this later on. So this arch was essentially a more stable arch than these ones here were. So this is all quite interesting. If you go back and look at the Kwok data, they didn't really see a lot of these strong sort of high frequency events. And that's partly because they were using ENVISAT data, which I think didn't have the temporal resolution that Sentinel-1 has. So they weren't able to capture events happening sort of on a timescale of a day or so, which we can do with the Sentinel-1 imagery. So this is another a sequence of SAR images. I'll run through this a couple of times. This is 2018 now. And what I want to do is when I run this, again, is focus on Nares Strait here, but also an event that happened out here in the Wandel Sea. So you can see here, we're now into February 2017. There's ice moving down through Nares Strait. It ceases sometime in March. You can see it's now ceased here. And I'm running it again now. And now I want to focus over here. So what happened actually in 2018 was a very large polynya opened up off of the Wandel Sea. And this polynya persisted for about 3 or 4 weeks or so, led to a very, very large area of open water. It wasn't actually connected to what was happening in Nares Strait, but it just again shows you how dynamic this area is. I think people tend to think of the last ice area as being an area where things don't happen. And that's not the case, at least now. One has these very dynamic events, transport down through Nares Strait, and also these polynyas forming here. So what happened in 2018 was quite interesting. So in early mid-February 2018, the Met Office forecast the presence of a sudden stratospheric warming. And some work I did with colleagues at the Polar Sciences Center showed that, in fact, this polynya that occurred in 2018, which is shown here, was the result of really, really strong winds in North Greenland. The winds got up to 25 or 30 meters per second. And these winds essentially blew the ice offshore. And what in fact was these winds were the result of this sudden stratospheric warming that occurred. And so this, I think, is an interesting example of how coupled the whole climate system is. So here's a sudden stratospheric warming event in the stratosphere, leading to essentially loss of sea ice in North Greenland. And so they're all connected together, just showing you again how tightly coupled the whole system is. So what happened in 2018, so that animation showed that the arch formed quite late. I think it formed in March that year. And it actually wasn't a northern arch, it was a southern arch. So we get arches forming both at the northern end of Nares Strait and also at the southern end of Nares Strait. And so in 2018, what happened is that one had a southern arch form across Smith Sound here. And you can see this is the monthly mean average sea ice concentration for May 2018. And one can see the presence of the North Water Polynya here, this area of reduced ice concentration immediately south of the ice arch. And again, it's the strong winds that blow down Nares Strait that are blowing the ice away from this region, leading to this area of reduced ice cover, which you know is the now. You see farther south in northern Baffin Bay, the ice concentration increases, and that's because essentially the now is limited in its fetch by essentially the high wind speeds that blow down Nares Strait. Once the winds get south of Smith Sound, there's no longer any topographic channeling and the winds weaken off. And so the now is sort of restricted to this region just south of the ice arch. So 2017 had a northern ice arch, 2018 had a southern ice arch in it. In 2019, NASA published this, they have this daily sort of things happening in the climate system, and they claim that the ice arch crumbled early in 2019. And as I'll show you in a minute, there actually wasn't an ice arch at all in 2019. So this is one of the problems of just looking at sort of sequence of satellite images on given days. It looks like there's an arch present here, and you can see here it's collapsing and here it's fully collapsed. But in fact, if one looks at the time series of ice area flux, you can see that there was never a stable arch, and there was a constant flux of ice down through Nares Strait. So one has to be careful. Sometimes when you look at just satellite images, they may not capture the whole story. And this shows you an example here. So these are four dates during the winter of 2019-2020. January 4th, you can see there's clearly transport down through Nares Strait. January 14th, the same thing. February 19th, again, transport down. And March 27th, again, transport down. So throughout this whole period, although there are some days like this one where it looks like there's an arch present, in fact, it wasn't stable. It never really led to no ice transport. And so one had continual transport through that whole winter. So in 2020, again, NASA published this image. I think they published it on June 3rd. And here one sees again, so in 2020, one had again a southern ice arch present. This is Kane Basin. This is the North Water here. And they made the claim that this arch was persisting despite a warm Arctic. In fact, that's the case. So this is of interest to us. So we put a flux gate here across the Bash Peninsula, across to Greenland here, and then studied the transport throughout the winter of 2019-2020 here. So this is the transport now across that flux gate. Again, we're starting in September 2019 and running through to July 2020. And you can see there's a couple of features present here. One had northward transport in October. Early winter, again, strong fluxing southward in early winter. The arch formed sometime around December 15th, but there was a period of about maybe a month, 6 weeks where it was unstable. One still had transport north and south, and then suddenly the thing locked in, and one had this very, very stable arch through to the beginning of July, where the arch collapsed, and then one again had northward, transport towards the south. What's interesting is that it looked like the collapsing of the arch was triggered actually by a northward transport event, which I don't quite understand why that would cause the arch to collapse, but it looks like that's what happened. So again, these are a sequence of, again, ice motion vectors. December 10th, the arch hadn't formed yet. This is January 27th. This was a stable arch, was present here. Again, through March, one had a stable transport with, again, no transport north of the arch. And these ice motion vectors are just essentially the first year ice, which is forming and being transported southwards. And this is then after the collapse had happened, and one now sees transport coming down through Kane Basin, moving southwards. So these are some Sentinel-2 true color images showing the collapse of the arch. So this is just before the collapse on June 25th. You can start to see there's a large fracture has formed here. This was the first bit of the arch to collapse in here. You can see some melt ponds is getting the ice is getting kind of weakened through here. There's some melt ponds present here. And this is essentially 2 weeks later. And one can see after the arch collapses, one has this huge flux of all this multi-year ice streaming down through Smith Sound into the North Water region. So the North Water is under pressure. Once the arch collapses, one has such as multi-year ice coming down, and of course the winds can't affect that multi-year ice away quite so easily. So the now tends to disappear once this multi-year ice starts coming southwards. I want to focus on this little feature here, which I sort of noticed when looking at some of these images. So it looks to be a little Polynya here off of the main North Water Polynya. And these are a sequence of 3 Sentinel-2 images, again, running through May and June. And you can see that the Polynya is present throughout this whole period of time here, okay? And it's kind of cool. It's off of the main North Water here, and it looks to be a persistent feature. And so, of course, you wonder, has anyone ever seen this before? And of course, the answer is yes. It turns out Sverdrup, who explored this area, first European to explore this area in 1903, noticed some artifacts, as I'll talk about in a minute, in this region. And he suggested this area had been inhabited for some period of time. The Oxford University had an expedition to Ellesmere Island in 1934, 1935, and they actually overwintered at a hut, which used to be an RCMP outpost. It's amazing that the RCMP had an outpost here in the early 30s, and it was just essentially on the Bash Peninsula, right in this region, right in here. And so these people stayed there. And so when Sverdrup came through, he noticed artifacts, and he suggested there was some long-term settlement in the region. Again, the Oxford University expedition spent time at this abandoned RCMP detachment, and the leader of that expedition was Edward Shackleton, who was the son of Ernest Shackleton. So again, a famous Arctic explorer who was the son of a famous Antarctic explorer. And so in the book that they wrote about their time, there are these 3 quotes which I think are really, really cool. So the first one is, "We descended again to the smooth ice of Flagler Fjord." So Flagler Fjord is the fjord at the mouth of which this Polynya forms. "After several hours, we reached the narrow bottleneck at the entrance to the fjord. Sakius, who was an Inuit who was with them, were so sleepy that we almost drove onto the thin new ice where the tide race swirled before they noticed it, and they whipped the dogs aside so they didn't end up in the open water. And then a few days later, he wrote, in the meanwhile, the open water upon which we relied for seal had frozen over. And then 2 days later, he said the ice at the mouth of the Flagler Fjord had again opened up. So they actually had observations. They don't actually mention ever it was a Polynya, but Shackleton actually was in this region, and he actually sort of, I think, had some very interesting observations about this Polynya. So this site was excavated in the 1970s, and they confirmed that the site had been occupied for over 4,000 years. So we're getting back into the Paleo-Inuit period in the pre-Dorset time. And the sort of suggestion was that the Polynya, with its readily available source of marine mammals, was probably the reason for the occupation. And in fact, when Peter Schleiderman arrived in the year when he excavated this region, he writes that they arrived at that region. There were a bunch of walruses kind of sunning themselves in this Polynya. So it's actually a pretty cool history. And I think from Shackleton's description, it sounds like this Polynya is associated with tidal currents in the fjord that may result in an upwelling of warm Atlantic water that melts the sea ice in this region. So again, it's kind of cool to think of that this site has been used for 4,000 years or so to essentially as an area where one could harvest marine mammals. So now I want to jump forward to just this past or this current winter we're in here. And these essentially are two flux gates. There's a flux gate across Smith Sound, and this is the Lincoln Sea flux gate to the north. And you can see, again, a positive transport. So one is transport southwards, and then around the 11th of December or so, the arch formed. The transport went to zero, and it's remained to zero throughout up until just a few days ago. If you look at the northern flux gate, one can see that even after the southern ice arch formed, one still had northward transport. And so what's happening, of course, is that the ice is still sort of moving southwards and it's converging along Nares Strait. And eventually I expect the transport will go to zero. It looks like it's going to zero here about a month after it went to zero in the south. And that's the time essentially it takes the information that there's an arch now present in the southern southern part of Nares Strait to propagate northwards and lead to a reduction in transport to the north. There are these two interesting events here where one had northward ice flux events. So there's one in mid-November and then one in just actually in the January 1st. And so these are interesting because, again, what's causing the ice to suddenly be transported northwards? So these are, again, two Sentinel-1 images with the ice transport on them. This is December 31st, and this is January 1st. And one can see, especially on January 1st, the very, very large northward transport that's happening here. If you look carefully, you can see that a small Polynya has actually opened up in the northern part of Robson Channel right in here. You'll also notice there appears to be sort of a cyclonic circulation up here, and we'll see this in the wind field in a minute. There was a low sitting off of here, and that essentially led to this large transport of ice north into the southern Lincoln Sea. So what I'm showing here, again, this is the ice area flux across the Lincoln Sea ice arch, and these are the wind speeds from ERA 5, so they're underestimated, but they have a good statistics. I'm showing 1, 2, and 3 standard deviations above the mean. And so one can see this event in November was associated with a 3 sigma wind event. And this event in early January 2021 is also associated with a 3 sigma wind event. I haven't shown the direction. Both these are actually our northward winds. Winds are blowing northward along Nares Strait. And so this essentially is what the 9-kilometer operational model shows for the wind speeds at 18Z on January 1st, 2021. You can see that, again, this really, really strong winds blowing north out of Nares Strait, and one can see the cyclonic curl here, and so there's a very strong deep low sitting here. There have been observations along at Discovery Bay and here going back to Greely's time in the 1870s, and he notice that essentially one had essentially very strong winds in Nares Strait, both northerly winds and southerly winds. And so this is an example, one of these very strong southerly wind events, which we think is responsible for transporting all this ice northward into the Lincoln Sea. So just to summarize this part, we essentially have now a lot of different sort of things that have happened along Nares Strait. So in 2016, 2017, there was a northern ice arch. It collapsed really, really early. It collapsed in May. That was the earliest collapse on record. There was no northern ice arch in 2017, 2018, but there was a southern arch present. There were no arches present in 2018, 2019, and ice transport happened throughout the winter. This is the only other event we know is 2006, 2007 from the Quoc data. There was no northern ice arch in 2019, 2020, but a southern arch formed. And then a southern arch formed again in just this past December. And what's interesting is we've had continued transport across the northern flux gate, leading to convergence of sea ice along Nares Strait, which I think will eventually stop sometime in the next few weeks. But of course, it's also interesting to look at volume fluxes and sort of come up with sort of mean annual values. So essentially, we used Quoc had developed a time series using radar-sat and Envisat-SAR imagery for this period of time here. We use the same essentially technique in our study, and so we combine these two to give us essentially a sense of how the ice area flux time series is changing over time. We use thickness data from Polynyas to estimate the ice volume flux as well. And so we have annual averages based from September 1st to August 31st of the following year. So these are the results. So the red values are from the Quoc study and the blue values are from our study. This is ice area flux, annual ice area flux. And you can see this is 2006, 2007, the year where no arch was present. And you can see that at least averaging over these 3 years, I haven't included 2020 yet in this data here, but essentially the average results over the last few years is the same as the maximum in the Quoc data. So there's been approximately a 200% increase in the annual ice area flux between the Quoc study and our study. This is biomass thickness data. And you can see, again, there's been this reduction in the thickness of the ice. And so when you combine these two, you get volume flux. And what's interesting, of course, is that now, unlike the ice area flux, 2006, 2007 stands out as being the largest ice volume flux year. But of course, the reason being is that the ice was quite thick back in 2006, 2007. And so the extra thickness, sort of the thicker ice led to a larger ice volume flux. But again, if you look at the average over the Quoc period and the average over our period, there's still been about 150% increase in annual ice volume flux. So we're seeing more ice area flux and also more ice volume flux occurring along Nares Strait recently. And of course, so there's two competing trends, of course, for the ice volume flux. Ice motion is increasing, but the ice's thickness is decreasing. And so so what happens, because we see the ice volume flux increasing, that means that the increase in ice motion is greater than the decrease in ice thickness. So we're seeing an increase in ice volume flux because the ice is moving more rapidly, even though it's thinner. Nares Strait ice volume fluxes, this isn't the case. There appears to be no increase in ice volume flux, and that means that the changes in ice motion and ice thickness are offsetting each other along Nares Strait, probably because Nares Strait doesn't have that thick ice, and so one doesn't have that extra effect that we're having here. So, as I mentioned, the work of Hibbler suggests that if you have thinning ice, you should have weaker arches, and so this is actually borne out. And so we used ice duration data. So Quoc also reported on the duration of his ice arches, and we also have the duration of our arches. And so this is data showing the duration of the arches. And there's 2 years where there were no arches present, so then you have 0 duration. And you can see again back in the QUAC data, most of the arches lasted for perhaps 200 to 250 days. Now they're averaging down maybe 100 days or so. And so if one fits a linear least squares fit to this data, one comes up with a trend of a reduction of about 1 week per year in the duration of the ice arches. So the arches are in fact not lasting as long, and that also suggests that they're not as strong as they were before. And so this is true also. I've combined the northern and the southern arches together. If you separate them, you get exactly the same result. So just to conclude then, we have thinning ice in the Lincoln Sea, and we had these very strong winds in May 2017, and that resulted in the early collapse of the arch. We expect that if we have continued thinning of the Arctic sea ice, such events will probably become more common even under less extreme wind forcing. There's evidence of an increased mobility of sea ice, and that's leading to an increase in the Nares Strait ice area fluxes. Unlike Fram Strait, the ice volume flux appears to be increasing as well, and that is leading and will lead in the future to an accelerated loss of thick multi-year ice out of the Arctic. The Nares Strait ice arches appear to be becoming weaker over time, and that's probably because the ice in the region is thinning. So the potential impacts downstream, if one has this multi-year ice getting out of the Arctic, one can lead to problems. This is a fishing vessel off of Newfoundland in May 2017, which was stuck in a large accumulation of multi-year ice that fluxed down through Baffin Bay into the Labrador Sea. And this little fishing boat was totally, it could handle first-year ice, but it couldn't handle the very, very thick multi-year ice. This is an interesting article was written on this work in the main newspaper in Nunavut, and they call this thing the plug, and they say that the plug keeping the Arctic's oldest ice in place is getting leaky. I think it's actually a really great way to describe that. I wish I was a person who writes captions, because that's a pretty cool one. And so that's got a tagline here is the loss of more multi-year ice through Nares Strait could threaten both the last ice area as well as the North Water. This is the Inuit word for the North Water. So I think this really sums up the concerns that have been sort of raised by this work, is that this plug is getting leaky, and that's going to lead to problems both for the last ice area, because potentially that ice will be fluxing down through Nares Strait, so we'll be losing that multi-year ice out of the last ice area, and also there are potential impacts on the North Water when one doesn't have these arches present and the thick multi-year ice fluxes down throughout the year, leading to issues with the North Water. So I'd like to thank you very much. And these are some of the papers that we've written on various aspects of this work, and I'm happy to answer any questions that you have. Thank you.
Thank you, Dr. Moore. That was a great presentation. And we're now ready to start the question and answer session. We do have several questions lined up in chat. As a reminder, if you're joining by Zoom, please do type your questions to the chat window and I will read them aloud. And if you're joining by phone, you will need to raise your hand by pressing *9 and unmute yourself by pressing *6 to ask your questions. I believe Dr. Moore will be available for about 5 minutes after the top of the hour if needed. So we'll get to our first question. That's from Megan Steele-Moore, and she asked, what will the future look like in, let's say, 20 to 50 years? Is there anything we can be doing now to help preserve the Arctic?
Thanks, Megan. That's a really great question. Megan is my daughter-in-law, so I really appreciate her listening, and she's always wanted to hear one of my talks. And of course, with COVID now, because she's in Vancouver and I'm in Nova Scotia, so of course we can now do things we couldn't do before. That's a really good question. So I think I think if we could jump 20 years in the future, 40 years in the future, we wouldn't have any arches present in Nares Strait. I think the ice is going to get so thin that one just couldn't sustain these arches. These arches are perhaps 100 kilometers long, and so there's a incredible stress that's built up in the ice. So one needs really thick ice to maintain that stress. And so as the ice continues to thin, I just don't think we'll have these arches present. We'll have continued transport throughout the whole year. That'll lead to probably a loss of multi-year ice from the Arctic. We will have lost all the the perennial ice from the Arctic, in 30 or 40 years, except in the last ice area. And so this leaky plug will potentially lead to even that loss of that multi-year ice. So that's, I think, quite concerning. The only thing that we can really do is reduce our use of carbon, right? And stop warming the planet up. And if we do that, then again, after some period of time, the Earth will cool down again, and hopefully we'll get thicker ice in the Arctic, and these arches can come back.
Oops. Sorry. And let's see, the next question was from Sergei Kirillov from the University of Manitoba. And he says, regarding the Sentinel-1 ice tracing algorithm within the Polynyas region, does it work for pieces of multi-year ice only? Is it capable to, quote, see, end quote, the new ice motion and therefore transport? Thanks.
Yeah, so this is Steve Howell and Mike Brady are the experts on the transport. I think it has a problem with sort of, it does better with ice which has a well-defined structure like the multi-year ice. I think it has more of a challenge to see some of the smaller features. So although you can get transport, I don't think there's as much confidence in the transports as you would have for the multi-year ice. So my answer is that it's more of a challenge to see the transport of the first year ice. Thank
you. And then Martin Jeffries asked earlier, when you're talking about the large Polynya on the north side of the islands, is it a Polynya? They're recurrent phenomena. Does this Polynya occur often during the course of a given winter and annually from one winter to the next?
That's a really good question. So we know that Shackleton saw it well, we didn't know what it was. I think from his description, clearly was there. We know the site has been settled for 4,000 years, and the assumption is the reason why they chose to occupy that site was because of the ready availability of marine mammals. So there's some evidence that the Polynya has been forming for at least 4,000 years. We look at it. I started looking at it. It's there most years now. Of course, the visual imagery starts, I think, in May, so we can't and it's hard to see in the SAR imagery. So it seems to be there most Mays and persists through to the time that the southern arch collapses, and of course all the ice fluxes out of the area. So it appears to be a persistent feature. Yeah.
Thanks. Next question was from Mikhail Shi. He says, have there been any instances where both a southern and northern ice arch have formed in the same season?
That's a great question. And I don't think it's possible because you need essentially that really thick multi-year ice. That's the stable stuff, right? So if one forms in the north, right, then essentially once you blow all the ice out of Nares Strait, there's no more thick ice to form a southern arch, right? And of course, if the northern arch doesn't form, then in most winters, not all winters, eventually, one gets that jamming up of the ice near Smith Sound. So I think you can have one or the other, but you can't have both. I've never seen both. Of course, our record only goes back 20 years, and who knows what might have happened, back when the ice was really, really thick. But my answer is no, I don't think you can get both of them. You just get one of them.
Thank you. Next question is from Wayne Roth, and he said, what are the currents that go through the Nares Strait?
That's a really good question. I'm not an oceanographer, so I will defer. There is pressures are higher in the Arctic than in Baffin Bay. So there's a southward current that flows through. There is some, the East Greenland current comes up around Baffin Bay. So there's probably some transport from the south as well, but I have to defer. I'm not an oceanographer.
Thank you. And then Andreas Preuser asks, do you have any thoughts on the potential impact of the massive amounts of new ice greater than 30 kilometers squared that formed in the 2018 Wandel Sea Polynya in just about 3 weeks? Sea ice budgets ocean relation. Is that?
So I think what happened in in 2018, once the Polynya so these strong winds blew all the ice northwards, and then it kind of relaxed back. The ice was still thinner because because just they lost some of the multi-year ice. So the ice, you could even see the next summer, the ice was still thinner in the Wandel Sea, but after that, of course, I think the signal just went away. So I think after, one season, you kind of lost evidence of it. So there was essentially the ice remained thin throughout all of 2018. But then once the next season started back, you essentially lost all signal of that Polynya, and it hasn't occurred since.
Thanks. Next question is from Jim Hannigan. He asks, might future work include looking at the years 2010 through 2016?
Yeah, that's really good. That's a good question. So I think we have RadarSat and ENVISAT SAR data for that period of time. We have tried to kind of stitch the two together, but there were some technical issues. I think the algorithm that Steve Howell is using, I think, is tuned up to work with higher frequency data, and so it has some problems with the RadarSat data. But it should be possible to go back and stitch together I don't know if all the period of time, but stitch back some of that period of time. That'd be quite interesting to do, because there is a big gap there, and a lot happened in that 10 years. So that's something that we thought about doing, but we haven't had some success in getting the ice feature tracking to work with the lower frequency RadarSat data.
Thanks. Doug Causey asked, how do these changes in ice flow northward and southward affect the upper water circulation in northern Baffin Bay? How do these interact?
That's a good question. I have no idea. I don't know. I mean, I think these, it was a surprise to me that one could have these episodic events where the ice reverses direction, and it's really the atmospheric forcing that's doing it. The winds are quite variable; they can blow either direction, but the impact, I don't know what the impact is on the ocean. I think it's really cool, but we haven't got that far yet.
Thanks. There are a few other questions, and I just want to confirm that you'd be willing to stay until about 10
sure.
after.
Yeah.
So I'm going to assume that some people need to leave, so I'm going to share some of the closing slides right now, and then go back to the questions. So for those of you who want to continue the discussion, we will stay online for another 5 to 10 minutes. For those of you who are leaving now, we want to thank you for joining us today and extend a special thanks to our speaker, Dr. Kent Moore. Today's webinar will be archived and available within the next few days on the ARCIS website, and that is on the screen right now. You can also visit the ARCIS homepage for more information about our programs and upcoming events. Next slide, please. Please do mark your calendars for 2 upcoming webinars. On Friday, the 12th of March at 9 o'clock Alaska time, Gil Bohr from Ohio State University will present the ecological insights from the new Arctic Animal Movement Archive, tracking 3 decades of animal movement across the changing Arctic. And on Friday, the 23rd of April at 9 o'clock Alaska time, Emily S. Chow from McGill University will present on the effects of climate change on seabirds. Next slide, please. We are always looking for ways to improve our seminar series, as well as suggestions for future seminar topics and speakers. Please take a minute or 2 to complete our short survey, and a link will be sent. A link is available now on chat and on the screen there. And we will also send this link in a follow-up email that you'll receive once this seminar has been posted to the archive. Okay, I think we thank everybody at the top of the hour, but we'll continue and go back to some of the questions that have come up. I believe the next question is from Martin Jeffries. And he asks, is the increase in ice volume flux, freshwater flux into Baffin Bay likely to affect physical oceanography of the bay? Are there any early signs of such changes?
That's a really good question, Martin. I think in 2007, I think Kwok noted there were some impacts on the salinity of the surface waters in Baffin Bay. So the answer is probably yes. But again, I don't think we've looked into that in detail, but it's a great comment.
Thanks. And then he mentions that his earlier question was about the Wandel Polynya off northernmost Greenland. I don't know if that changes the answer that you gave. I don't think so. And Harry asks, or he just notes that Ron Vincent from the Royal Military College of Canada in Ontario has written several papers about the Nares Strait ice arch, very similar to your work in remote sensing 2020. Ben Holt asks, did Greeley have any observations of the Flagler fjord and surrounding area that were relevant to the small Polynya?
That's a really good question. You know, they marched by, right? But I haven't. I mean, I have the Greeley report. I actually haven't looked into. That's a really good point. I don't know. I don't know. I think they, you know, that fjord's a bit inland. If they were really moving along the coast, they probably wouldn't have got in that way. But that's a really good point. I'll have to go back and read and see what he does, because they walked right by there. So maybe they did, and that would be really cool as well. Thank you for that.
And Martin Jeffries asks, are there additional insights to be gained by investigating ice dynamics, motion, rheology along the length of Nares Strait over the course of many years? There ought to be plenty of SAR data available to do this.
I think it's yes. That's, you know, I'm not an ice person, but I think there's some really interesting things happening, especially the fact that it looks like some of these collapses are caused by not what I would have thought would be north-southward winds blowing south. There's actually kind of northward winds, I think, putting extra stress on the ice, which when they relax, the ice collapses. So I think there's some really interesting stuff that goes on that needs to be looked at, but not by me, because I'm not a rheologist. So.
And Andreas Preisser makes a note to everyone saying there, and especially to Martin Jeffries, there are some winter seasons where the ice opened up in the Wandel Sea prior to 2018, but the extent in 2018 was exceptional. And Ann Jennings asks, if the northern ice arch forms, does that allow the now Polynya to form, or does it weaken the now?
So that's a really good question. So we're kind of looking at that, and the general consensus is that once that you need a Smith Sound ice arch to get the Polynya to form, but when the northern arch forms, essentially the same thing happens. You essentially, you know, you essentially flux some sea ice down through Nares Strait. It's thin stuff. You can easily advect it away. So the Polynyas appears to form in the years when you have a northern arch present as well. The years where it's under more pressure is when you don't have any arch present, because then throughout the whole winter you have this multi-year ice coming down, and that's a problem because the winds can't blow that ice out. So the ice tends to persist in the region. So I think Dave Barber has sort of suggested that we may be transitioning to a time when the north water becomes more like a marginal ice zone, where there's essentially ice present throughout the whole period of time. You don't get the really low concentrations. But that's a question which I think is one that we can look at now, because we at least have 2 years where there's no arch present, 2007, 2019, and then a couple of years where the northern ice arch. So one thing that I actually want to do is try to understand the impact of these various flavors of arches on what the Polynya looks like. That's a really good question.
Thanks. And Tom Ballinger asks, thanks for an interesting talk, Kent. Are you seeing much of an ice arch response to the large-scale atmospheric circulation extremes in recent winters, extreme positive AO in 2020 and negative AO in recent weeks?
Yeah, I don't know why the arches form or why they don't form. So I think these are things which are all, I mean, I've looked, is it cold winters? Doesn't appear to be cold winters. Is it thin ice? It doesn't appear to be thin ice. If you looked at one of my earlier slides, I showed that 2017 had really thin ice, but 2018 and 2019 had similarly thin ice. So it's a nuanced question. I don't know I don't know if it's dynamics or thermodynamics that causes the arches to form. And that's something which we're trying to look into, but it seems to be like not a single thing, but more than one thing that are happening to have these arches present or not. So I don't know. In fact, I don't know whether, you know, like for instance, this reversal that happened in early January, I don't know if that had something to do with, you know, the, you know, changes in the large scale circulation. They're pretty transient. So there was a deep low that kind of transited north of Lincoln Sea, and I think that caused the strong winds. So it's probably more local events rather than these large scale teleconnections, but I don't really know the answer to that question.
Thank you. And Wayne Roth asks, what is the oldest ice now in the Arctic?
That's a really good question. So with the microwave data, I think you can tell ice which is greater than 5 years old. So there's a bunch of ice which is greater than 5 years old. I assume there's ice which is a lot older than that, but I don't know whether I don't know what the oldest ice is in the Arctic. It's not as old as it used to be for sure, but there's a lot of ice which is at least 5 years old, and that's the oldest that we kind of distinguish with the microwave data.
I don't see any further questions, unless there is something else that someone wants to share on the chat. Dr. Moore, are there any last minute comments you wanted to make before we close?
No, I just want to thank you for this opportunity and for all the great questions.
It was a really good conversation today. So we'll go back to a couple of those slides. I just want to remind people that we will have our webinar archived, and ask you to give us some feedback on today's webinar. If you have time, that link is both on the screen, and I believe Kuba shared it earlier, and is shared right now in the chat. So you can go to that evaluation survey. We really do appreciate information like that. And we've got the 2 webinars coming up in March and April. And with that, I do want to thank everyone for joining us today, and especially Dr. Kent Moore. Thank you so much for really good presentation and great information.
Thank
So
you.
wishing everybody a good day and the start or continued good luck this week. Thank you. This will close our webinar. Bye-bye.
Bye now.